I started it. Okay, everyone, hello. Welcome back to SAT Math Question of the Day. Here's our question of the day. It comes from the SAT Educator site. It's considered a hard question. Spoiler alert, this could appear on a Blue Book test. The graph of 7x plus 2y is negative 31 in the xy plane has an x-intercept at a0 and a y-intercept at 0b, with a and b are constants. What is the value of b over a? You know what I would do? I would just go right to go to Desmos. I know that you and I, we never grew up this way, but I would consider doing this on Desmos. Just typing in 7x plus 2y is negative 31 at Desmos, graph it, and pick off the intercepts, and then divide the y-intercept by the x-intercept and do it. So, should we just do that first, or should we do it algebraically?
Go ahead, do it.
Okay, I'll do it algebra. Okay, so now this is going to take well, when you do Desmos, you can open it up and still keep the screen available, so you don't have to actually type it, but I'm not going to be able to do that, I don't think. So I will actually write the question out, y over x intercept. Okay, so I wrote it out. Desmos, we have to basically make us smaller, so just bear with us. Oh, I'll just make us real tiny. Come on, make us tiny. Oh, so frustrating. Okay, here we go. What are we going to do here? We are going to graph 7x plus 2y is equal to negative 31. There we go. Okay, we got it. Now we have to blow this thing up, and we have to pick off the intercepts. Not bad. So it's the b over the a. So it's this thing. Whoa. So it's negative 15 and a half. Okay, fine. So we'll write that down. Negative 15 and a half divided by what? What a weird number. Okay, whatever. 4.429. There were sevenths involved. I don't know if you remembered what the thing looked like. Actually, we could type it in here. We could do... and the answer is going to be positive because there are two negatives. Okay, so we just have to remember that. The answer is going to be positive. 4.429 is equal to 3.5. So the answer is 3.5.
Which is...
So the answer is D. Okay, well, oops, seem to have lost us. Bear with us for a second. Bear with us for a second. They seem to have... Zoom. Once we change the settings, all of a sudden, I'm just trying to change the way we look. Okay, yeah, so that's one way to do it. That's a pretty good way of doing it. Is just do a graph, just do it on graphically. But in terms of what's going on, you have a. Right, today's not the day for computer stuff. Okay, so. Okay, great. Okay, so you basically have a graph. We already know that it looks like this, but knowing the equation, you can't necessarily tell immediately what it is. It does have a negative slope, and they're basically looking for the x and the y-intercept. So what you could do is you could go x, y, and you can make this a 0, and you can make this a 0. Okay? And now I always get confused. When the x is 0, that is the y-intercept, so that's b. Oh, it says right there. A. So then you just plug x equals 0 into here. So you solve for b. So b is negative 31 over 2. And then you do the other thing. Now it's messy. You make this be 0, and then you solve for x. So it's negative 31 over 7. Complex fraction. If you don't do it out graphically, you have to know how to do a complex fraction. There are two different ways to do a complex fraction. We'll do the more traditional way. negative 31 over 2 times negative 7 over 31. You cross off the 31s, the negative signs make a positive sign, and you have 7 over 2, and that's the answer. So, those are the two ways. Those are two ways to do this problem.
Thank you.
Okay, Seth? The way you said thank you sounds like you have another way. Good. Okay, you can tell so much communication by the tone of voice and the expressions of people. You can tell immediately Seth knew another way. Let's hear it. And let me take off some of the stuff so that the problem is not.
Get rid of all.
Yeah, get rid of everything. Seth doesn't like the way I did this, but let's hear it. Seth, go ahead. That's why we're here. Let's have some other approaches and other insights into this. I tend to do things straight out.
Well, here we go. Start.
Let's go.
Here we go. Well, here's the equation. So what's the slope? Well, convert it to, put the x on the right side. 2y equals negative 7 minus 31. I don't care. Minus 7x, right?
Yep.
And so the slope is equal to negative 7/2.
Right.
Right. Now, then draw a little picture. The typical x-intercept and a typical y-intercept.
Yep.
Typical y-intercept. Right?
Yep.
When a and b are positive, it has a negative slope.
Right.
And that slope is minus b over a. Right? So what is b over a? B over a is the negative slope. Okay? But we figured out that the slope is minus 7 too. So the negative slope is plus 7/2. That gives it there.
So in other words, you did it. So what you did is rather than calculate B independently of A and then divide them, you went directly for the ratio of B over A, never ever calculating what A and B actually
That's
are.
correct.
Only the ratio. Right.
Yes.
That is a great. Anytime you're asked questions on
I kind of quickly realized that ratio is related to the slope. And then I had to visualize this picture to realize that ratio is the negative of the slope.
That is a little confusing.
So to answer the question, what I decided to do was find the slope of the line from the equation, and then remember to take the negative of it.
Right. Or
now the slope happens to that equation. The slope is negative. The negative of a negative is positive.
Right. Right.
Yeah.
The other way to view it a little bit more methodically is this for sure because you figured it out. We are solving for B over A. Then we care about B over A, so let's solve this equation for B over A. So if we solve this equation for B over A, we want to solve for this. There's a -1 bothering it. So we would divide both sides by -1 and multiply both sides to -1 to say that, you would write negative B over A is slope.
That's no. It's by the time you're taking the SAT, this relationship, it's a good idea to be able to figure out this relationship immediately.
Seth, you have a PhD in math. You've been doing this a lot more years than almost every high school student.
Yeah.
So, most people, I only have a PhD in mechanical engineering. I wouldn't have, I don't know if I would have, I guess maybe I would have seen it that fast, but I would have taken the more methodical approach. But you have a lot more experience in math, right?
I don't know. I'd like, we should survey what high schoolers, what high schoolers can do.
Yeah, I'll tell you what. Please, if
and I think the deal is the SAT is a test of how much the high schooler has done algebra problems. When you do algebra problems enough, you run into this kind of situation many times over and over and over again, and then you realize that there's a pattern, and it's a pattern that you would learn to recognize right away, right?
You know what we should do?
And so I think you should. My advice is to you use the system when you're not sure why that a relationship like that holds. But once you do the multiply by -1 on both sides thing, and you realize that's when you have a equals, and then a equals minus b multiplied by both sides by -1, you get minus a equals minus of minus b, minus of minus equals plus.
Yeah.
You realize that that's directly that a equals minus b is equivalent to minus a equals b.
Okay, but you okay? I mean, okay. So
my advice to the audience.
Okay, go for
it. You prepare for the SAT. Prepare for the SAT. This relationship should be available to your mind. Bingo.
Fluently.
One step.
Fluently.
Yeah.
So why don't we do something we've never done before? Why don't we ask the people who are watching this, particularly if you're in high school, if you're a high school math teacher, or you're a math teacher, or you're just watching this to fall asleep, please don't have to answer it. But if you are in high school and you watch this video and you got this far, which is possibly unlikely, because most people don't watch it that long, why don't you leave a comment and tell us which way you would have done this problem, or let's say you did it and you pause the video. Did you do it method A? Well, method 1. Method 1, the graphical approach, which is the first one we did. Method 2, algebraically. Solve for B, solve for A, and divide. Okay? And then that way you solve for A and B independently. You get the two intercepts and divide. 3, you do it the way Seth did it. Solve for B over A to solve for literally B over A, not caring less what A and B actually are, but only their ratio. And let's see. And then in a few days, we'll report back. Just, we'll spend a second reporting back. So let's see what people say. But in general, when you see a problem anywhere in math where they're asking you for either a ratio or some combination of variables, it is well worth your time to at least try to see, is there a really nice way to get that ratio or that subtraction or that combination of variables directly, as opposed to actually having to solve for each variable and then doing the math. That's a very, very classic question. By the way, this question is so classic SAT. love questions like this. So be ready for things like this. And sometimes it makes sense to solve the B and A independently, like I did those first two methods. And sometimes it makes sense to do it the way Seth did it. It really comes down to how much time does it take you to be clever. If it doesn't take that much time to be clever to get the B over A directly, then do it that way. If it takes too much time to think, wow, how can I be so smart, then don't bother and just do it classically. Just solve for B and A. So, yeah, I mean, basically you have to know what the intercepts are. Well, in the way I did it, you have to understand what the intercepts are and how to get them from an equation. So, I'm sure there are other ways to do this too.
Oh, there's another, let's see, A and B in the slope. Yeah. You want to find the ratio of the intercepts. Okay.
Yeah. The other, for those people who hopefully you are not doing this, but you can memorize, given an equation in standard form, ax plus by is c, you can actually memorize a formula for the slope and the x and y intercepts as formulas. Highly unsuggested because it's not that easy. It's not that hard to get them on the fly. But that is possible.
Well, yeah.
So let's do the 4 questions and let's see how they do it. Well, we will see how they do it. They probably did not do it graphically because they probably don't want to show it graphically. So calculator doesn't really help here. Can you start with the answers and back check? Not really. How does this differ from a school test? Some teachers do ask for ratios. If you're at a higher level algebra class, you will see this question. If you're at a lower level algebra class, you will not. You will just see, well, what's the A-intercept, what's the X-intercept, or what's the Y-intercept, not the ratio of them. Is there a pattern to this question? I mean, are there specific numbers in this question which form a pattern? Not really. The pattern is more conceptual, so it doesn't really count. The pattern would be the essence of the problem. And what are they asking for? What did the committee want to see if you knew how to do? Well, it depends on how you did the problem. Right off the bat, it looks like they want to see if you can calculate. First of all, they want to see if you know how to get the x and y intercepts from a linear equation that's in standard form, and then how to follow instructions, b over a, and also how to deal with negative signs. If they also may want to, and if you do it graphically, they'll want to see if you know how to graph an equation and pick off the intercepts. And then if you, I don't know, Seth did it a real smart way, where you could see the pattern that the b over a is related to the ratio of these two numbers by this method, which, Seth, it's wonderful how you just proved it first before saying the relation, because that's the right way to do math, is to show it first as opposed to say what it is. Say that
I did say it first. I didn't.
Yeah, maybe, but you also showed it graphically.
No, again, it's like, yeah. Well, it's one of the some people like math because some people say that they like math because you don't have to memorize anything. You could derive everything.
Yeah.
Well, that's not true, because in practice, it takes too long to derive everything, and you need to know, to have facts that you perhaps had derived in the past. You have to have them available in your mind to use them.
Right.
And so it's so that's it's a short-sighted and not really realistic. It's not an attitude that is helpful for doing increasingly difficult math.
And Seth also used something I've always talked about in terms of different languages and modalities of thinking about algebra. Seth invoked the geometric modality to explain how he did the problem. So he went from algebra to the geometric approach, to the graphing approach. Sorry, the graphing approach, the graphing modality, and then back to the algebraic modality. It's sort of like a language, a different way of thinking. Very useful. Please train yourself to switch and be fluent in these three, what I sort of call languages. They're not really languages, but ways of viewing algebraic equations, both algebraically, graphically, and using a table. Tables don't come up that often, but try to just recognize that there are these three different ways of thinking, and in some problems, one way of thinking is better than the other. Okay, so there's always something in every problem. That's what we do. We try to bring in different approaches to the problems and different insights, because you never know which insight and which approach will work best for the problem they will give you on your test. Okay, so let us see how they do it. Oops, so today we have, because we switched to the graphical approach, we had to switch screens. Right now we're a little bit screwed up. Okay, so let's see. This is how they say it. So they did not do it your way, of course. Of course not. They did it more my way. So let's see. The x-coordinate can be... Wow, this was method 2. Again, please tell us which method worked for you. This is method 2. Okay, this is method 2. And then they have... Oh, yeah, they also... I'm sorry, but if you do method 2, the committee is also seeing if you know how to do a complex fraction, which is this messy thing. How do you deal with this? You just review a over b divided by c over d is a over b times d over c. Some people say keep, change, flip. Did you ever hear the word keep, change, flip, Seth?
What?
Did you ever hear the method keep, change, flip to do a complex fraction? Keep, change, flip.
Well, the first word is keep, K-E-E-P?
Yeah. Keep,
No.
change, flip. Yeah, either did I. There's a more modern way of it. It's taught. It's a keep, change, flip thing. Anyway, that may ring true to some people. By the way, there is another way to do this. We never learned it. Maybe it's a more modern way. You multiply top and bottom by the common denominator of 14, which is not the way we learned it. You can multiply top and bottom by the common denominator of 14, and that blows off the fraction. So it's negative 31 over 2 times 14 divided by negative 31 over 7 times 14. So this is negative 31 times 7, and this is negative 31 times 2, and the negative 31s cancel, and you have 7 over 2. You never learned it that way, right? Multiply top and bottom by the common denominator?
Yeah.
Yeah, which way do you do it? Given nobody telling you
The
how to
way
do
I do it, the way I do it is let's see here we have minus 31 over 2 over minus 31 over 7. Well, the way I do it is that I know the pattern.
Okay.
That if they're equal numbers,
Yep,
in the same spot of the numerator fraction and the denominator fraction, I could cancel them.
okay.
And then I know that a 2 in the denominator of the numerator becomes a 2 in the denominator of the simplification. and the number in the denominator of the denominator becomes a number in the numerator, and there are two negative signs. Right. And that's how I do it.
Okay. But notice, there's a pattern there. The fact that the 31s are the same, right?
Yeah.
In
other words, I do not go through the step of converting that to 31 over 2 times 7 over 31.
Right, yeah. Because
I just do it right there where it's written.
They're going to cancel anyway, right?
Yeah. However, using this technique, I've made mistakes. And indeed, I think one could avoid making mistakes by explicitly convert, especially in more advanced math, these four things: numerator of the numerator, numerator of the denominator, denominator of the numerator, denominator of the denominator. We work with cases where all four of those things are polynomials.
Yeah, right. They're complicated. Yeah.
They're complicated, and then you want to throw out, cancel common factors in polynomials where they can be canceled.
Right.
Yeah, but then you have to remember to flip that when you finally simplify it, you take the appropriate things in the denominator and put them in the numerator.
But you also have to remember with polynomials that you can't have any denominator equal to 0. So you have restrictions, and once you start crossing stuff off, you have to also remember those restrictions. But if you have everything as a denominator, then it'll be more in your face.
The thing is, if there's a common factor that becomes 0, the common factor in the numerator and the denominator, when it becomes 0, versus canceling it out, what happens is the limit values are the same.
Yeah.
It's called a removable singularity. You don't have to worry about that when you do it with time.
No. But teacher, the question may say, what are the values what is the domain of this expression, or what is the domain of this function?
You could say, but professors.
Yeah.
Say that you have this expression that's undefined at a certain point in the domain. You could extend the definition so that to extend this definition that's missing at a point to a definition of a continuous function.
Oh. Okay, you mean?
And in fact, that is a step that's taken. It's a step that's the step that's taken when deriving formulas for the derivative.
Yeah.
The thing is, with the derivative, when you evaluate it for the small increment equals 0, the ratio is undefined. But the beauty of it is that it's well defined near the point where both numerator and denominator become 0, and so you define the derivative as the limit.
Okay,
but then when you do the calculation, you simply cancel. You cancel two polynomials. You cancel x minus a against x minus a. And that's good for every x except for a. But after you cancel it, you get an expression that expresses what you get with that ratio as you approach, when x approaches a and it approaches the point where it's undefined, the value approaches what it is if you cancel it.
Right. So let me just ask you.
So canceling two polynomials in situations where they can become both zero is done all the time.
Wait. So let me just ask you a real simple question. We're not going to talk calculus, okay? Well, maybe we will in a second. Well, we're not going to talk calculus. All we're going to talk about is continuity. Is this function continuous at x equals 2? This function right here. Is it considered mathematically, technically, is this function continuous at x equals 2? Yes or no?
Well,
yes or no?
It's at x it's undefined at x equals 2.
Okay, so that means
you can't say whether it's meaningless to ask whether it's continuous.
So the answer is no. It doesn't meet the criteria of it being continuous.
Well, right? Does the criteria being continuous is
yeah, we have to go
I don't know. You know what? To do that, to answer this question, we have to get a more careful definition of continuous.
Let's bring in the biggest book on the bookshelf. Stuart, look at the size of this thing.
Okay, let's see. Look up the definition of continuous.
You always judge a textbook by how many pages it is, right, Seth?
Yeah.
So let me just see. How many pages? This has 1,200 pages plus appendices. So this thing has like 1,400 pages. Okay? So therefore, it's a good textbook. I mean, obviously, I'm only kidding here. Okay, continuity. Limits and derivatives. Derivative function. No, it's before that.
Actually, I think in terms of topology, even if the function is undefined at x equals 2,
yeah,
what we have is a topological. The domain of the function is the real line with 2 removed.
Yeah.
And then, so we have a function from the real line with 2 removed into reals. And when the definition of continuity from topology is applied, the answer is yes, it is continuous.
We're not doing topology. We're doing calculus.
So you have to look up that calculus definition.
I have it. I'm going to read it. Ready?
Okay, what does it say?
Okay. Right here. See, I'm not cheating. Page 114. A function is continuous at a number a if the limit of the function as x approaches a is f of a. Notice the definition 1 implicitly requires 3 things if f is continuous at a. 1, f of a is defined. That is, a is in the domain of f.
Okay.
So it fails, right?
Okay.
Yeah.
Good.
And the limit exists, which does, and the limit as x approaches a is f of a. So it fails. It is not continuous, but you're right. It has a removable discontinuity, though. I think that's what it's called.
Okay. So indeed, that's interesting. Yeah. So that calculus definition actually it comes out differently.
Yeah.
In the case of a definition from topology.
And then just to mention calculus for a second, that means it's not differentiable either at x is 2. Because differentiable means it also has to be continuous at the point.
Yeah.
So, that's it. Okay, so we went a little bit deeper into some stuff, but that's okay. So, I'm Joel. I have a PhD in mechanical engineering. My brother Seth's a PhD in math. Thank God he's here today because we asked him some pretty good questions about this stuff. Seth came up with being a PhD in math, he came up with a really great way of doing the problem by solving for B of A. Anyway, that's why we're here. We offer different approaches on doing each question, and we really try to go into detail into every question and go over different things you should know. We don't know what's on your test, but we do know that these concepts, these ideas, the stuff the material, the concepts are going to be on your test. Particularly, they love these questions where they have an equation with parameters, and then they ask you questions about what those parameters are, or ratios of these parameters related to these linear equations and quadratic equations. They love these questions. So be prepared for these things and practice. Take all the Blue Book tests. We heard rumors that Blue Book 4 and Blue Book 6 on the math side are the most closest to the actual SAT. Pay particular attention to those. And keep practicing on the Khan Academy digital course, because they partner with the SAT, so presumably those questions are very much related to what you'll see on the SAT. Yes, Seth?
Okay, I'm just bumbling.
Bumbling. Okay, I guess that's it. So please,
that's it.
Please dislike our videos. Please leave comments, particularly today. Please let us know how you would have done this problem or how you would do this problem. We really want to know. It really helps us. Okay, everyone, I think that's it. Yes, and if you have any SAT math questions, please email them to us at satmathquestionoftheday@gmail.com. I guess that's it for today. Okay, everyone, have a great day. Bye-bye.